Hello folks, this is the video tutorial for chapter 9 of my textbook, Composites Finite Element Analysis Essentials for 3D Experience, release 2021x. The title of the chapter is Frequency Response of a Clamped Composite Plate. So first let me explain to you what the problem is. We have a square plate which is clamped on all four edges. And right at the center of it, in the middle, you have a mass imbalance that's turning at an angular velocity. You can imagine that it's a fan, and the fan is there's a flaw in for example one of the blades, and the fan is exerting a force, a periodic force or a sinusoidal force in the vertical direction. Okay, this composite this composite plate is made out of 4 plies, so plus minus 45 degrees, and it's symmetric. Material properties are exactly what we used in chapter 7. Chapter 7, actually, geometry was the same. Material properties are right here. And the only difference between chapter 7 and this chapter is that there we applied I believe, a constant pressure. Okay, right, on the plate. Okay. Now, because this is a dynamic problem, we have to specify the density, and it's right here. And the dimensions are 500 millimeter by 500 millimeter, and the thickness of each ply is 1.25 millimeter. Okay? Now, I have to say a few words about the nature of the loading in this problem. If you look at your vibrations stuff, you see that if you have a mass that is a distance away, say b from some center of rotation, and this is turning at the angular velocity omega, the centrifugal force is mb omega squared. Mb omega squared. Okay, so you notice that this force, this centrifugal force, because of the fact that it's turning, it's actually exerting a sinusoidal uh, load in the vertical direction. Okay, so it's going to be right here. You can see that the value of f naught omega is constant. It's right here, mb omega squared. However, because this is turning, the vertical component of that centrifugal force is sinusoidal, like this. Okay, these are the kind of thing that you do in a vibrations textbook or a course. Okay, so I'm assuming that the mass imbalance is 100 gram, and it's a distance 20 centimeter away from the center of rotation. You put the stuff in here, and if omega is written instead of radians per second in terms of hertz, then it's going to be right there. These numbers this number 0.0079, and the fact that we have an f squared here is going to be used later on in 3D experience. Now, what I need to do is that or f squared, I have to create an amplitude which at frequency 0, of course, is 0, and the range that we're going to look at in between 0 and 300 hertz. If we look at 0 and 300 hertz, then the amplitude function that we're going to define is going to be something like this. I have to give this curve to 3D experience. Okay, so and instead of typing it line by line, I've created an Excel file which is exactly this curve, as you can see, from 0 to 300. Okay, and at 0 is 0, and at 300 it is 1. That's right here. Okay, so I'm going to be using the Excel file. This is already created and I'm putting there. Notice that on the first row I have X in hertz, parentheses, hertz, parentheses closed, and Y has no units. Okay, you can see that it has no units. All right. Okay, so let's go ahead and make the part. First of all, I renamed this thing properties, and I'm going to call this video chapter 9. So this is going to be video chapter 9. Okay. All right, and it's a frequency response. I'll put down FR here and say OK, and ready to make. So on a convenient plane, on that horizontal plane, I will sketch a square which is 500 millimeter by 500 millimeter. And let me do this thing. I'm not sure how I do it in the book, but it really doesn't matter. Well, yeah, okay, let's center it. Okay, I think I'm centering it in the book. So that, let's dimension these things. So this is 500 millimeter, and this guy is also 500 millimeter. All right, and we exit and we fill it. So we go to the surface tab. Here is fill, and we say OK. So there we are. Okay, so let me save this thing first. And I'm going to create an access system right at the center here. So we go to Essentials. Here's an access system. By default, it puts at the global origin and align with the global coordinate system. If you want to move this thing or do rotations and things like that, you have to do that. But this is fine for me. I don't need to do any of those things. Okay, good. There's access system 1. The next thing is we're going to create our material properties. So we go to the tools, create a material. Let's give it a name. So video chapter 9. Chapter 9. Frequency response. Now we say OK. Let's give it a second. So it's going to create in the material database right there. It's going to create something called chapter 9. Okay, maybe what I do, I save this thing and then look for it to your browser. Now I should be able to find chapter 9, video chapter 9. There we are. Okay. So now we're going to input the stuff. So right click, composites, unidirectional, although this is cosmetic, it doesn't do anything. And the thickness is 1.25 millimeter. And we say OK or close. Now we're going to input the moduli, different moduli, fiber direction, transverse direction. Right click, simulate. It's the structures, Abacus Multiphysics. We need the density, and the density I believe was 1800 kilogram per meter cube. And for mechanical elasticity, elastic, and this is a lamina, so we're going to change this thing to lamina, and we put in those numbers that we had in the table. So let me see now. The first one, I'm going to look at my table here. Okay, E1 was 148 gigapascal. Okay. E2 was 10.5 gigapascal. Mu was 0.3. G12 was 5.61. And this is also 5.61 because these are unidirectional fibers are usually are in fact what they call quasi-isotropic. Yeah. Okay, and this one is half of that, 2.8. Actually, I didn't mean to say quasi-isotropic. I meant to say transversely isotropic. That's okay, 20.2.8. And this is pretty much it. So we say okay, and now we're going to apply this thing to our part. So apply, right-click, apply. We don't need this thing. I minimize it or close it, and then apply it to this part. You can see that it was applied here, and if you check it, you're going to get the values that we inputted. So we say close and save. All right, we did this layup last time in chapter 7, but we're going to do it again. So we go now. Let me remind you that whenever I do these things, I also bring this material as a tab up here so that I can seamlessly go back and forth between the part and the material if needed. And here's the way you do it. You go there, top left corner, and you find this uh, application, which is called material definition. What happens is that it uh, immediately puts the material that is in session. Maybe you have other programs, other uh, parts also made, so those are also in session. But here, this is the only part that I made presently. So it takes the material. There's a tab here, it puts it there, and this is my part. Okay, then I don't have to go back and forth in the searching the database. You can easily access it. Okay, good. So now we're going to go to composite design. All right. Notice that down here, the icons and the action path change. So we're going to do this thing as a ply approach, manual ply. And you click on it, click on the composite parameters. And notice that one of the things that you have to do is add a material. And you click on it, add the material from the database. Now, all you have to do is to go to this tab. Notice that you cannot pick it from here. You cannot pick it from here. However, if you go to this tab, then you can select it from there, okay? And it will populate your composite parameters dialog box, okay? Now rosette, we created, add a rosette. Remember that the access system that we created. We say okay, and that's pretty much it. So we close this, and if you look, here is your rosette. So 0 plus minus 45, 90. Okay, good. So let's save everything. And now we're going to create our ply group. So this is the surface. I use the draping direction upward default. Say OK. And now we're going to create my two plies and then mirror them. OK. So ply number 1, put it in there. And the boundary is, or the contour is that sketch that I created right there. You see this? The first ply is 45 degrees, starting from the bottom all the way to the top. Ply number 1. The next one, ply number 2, in that ply group, same boundary, sketch, and minus 45. Say OK. Now I have created two plies here. They're in that sequence, okay? And I'm going to mirror it, symmetric ply stacking, and I select that ply group. Non-pivot means that 45, minus 45, minus 45, and 45. If you say pivot means 45, minus 45, 45, you know? So that's what I want, 4 of them. You can always check it. You go to review and you say apply exploder and you say apply, and these are the 4 plies, okay? Cancel because I don't need it. All right, let's save everything. Now, before I go any further, because now I have to, well, it's okay. So let's go ahead and mesh this thing. So we go to structure model, default, select the defaults. Okay, and let's do the meshing first. So you go here, you select the mesh, you select that. Oh, what I meant, you use the surface quad mesh, surface quad mesh, you select this. And 25, that means 20 in each direction, 25 millimeters. Remember, this was 500 and 500, so it's going to be 20 in the horizontal direction, 20 in the vertical direction. And there's nothing else to do. Parabolic element, you say mesh, and there we are. You say okay. All right. Then we're going to define the section properties. So to do that, you have to switch to model. From mesh, you go to model, and then under properties, you go to shell sections, and you say composite shell section. Select it. The support is that fill. You can use that fill, okay? And we're going to do it by plies. By plies, it says, well, where is it? Well, there's only one ply group that I have. It's right there. And don't forget to go to the advanced and make sure that the offset is none. That means offset of none simply means that these 4 plies, place them symmetrically about that plane. Okay, no offset. That's good. Okay, notice that the nodes have been created, the properties are there, and we just save this thing. Now the next thing is we're going to go and apply restraints and loads and things like that. We have to go into scenario and do that. But before you do, I make a point of reminding people, hide the sketch, hide the stacking. I don't think you need to hide this thing, but I'll do it anyways, because I don't want to end up taking an edge, for example, and say clamp, and that edge happen to be, for example, the the edge of a ply, okay? So that causes a problem. All right, the other thing is that if I don't want to see my elements here, right click, visualization management, just don't show me the element. So go to FE model, don't show me the element, just show me the geometry basically. Okay, so now we're going to go to scenario, structural scenario creation. Now we're going to do this thing as a what is called a harmonic response, or frequency response, or sinusoidal loading, or linear dynamics, steady state linear. These are all the same thing. Okay, they all have the same meaning. So say okay. In order to do that, I have to extract the frequencies first, because it's based on modal superposition. So I need to extract frequencies first, and then use those frequencies to do whatever I want to, I'm after doing. Okay. Now, there is one other thing that I would like to mention, and that is, remember, at some point, I want to go and plot the vertical displacement of this center node, okay? In fact, not as a function of time, but here the amplitude of this vertical displacement as a function of frequency. Now, in order to do that, I need to create a group. And as a matter of fact, later on, I want to apply a force at that center point. In order to do that, I have to create a group. So why don't we do that? Why don't we do that now? So let me hide all the stuff that I don't want. Hide the access system, hide these planes. Well, actually, I will leave that those planes there, because I know exactly where the center location is, right there. Okay, good. So let's switch. Let's go and create our group, and the groups cannot be done here. You go back to model. You go back to model. I'm sorry. What I meant is, let me see now. You go back to the model. Yep. Oh, okay. Well, we're gonna have to create our model, and then okay, we're gonna have to create our model, and then the group. So we select that finite element model. Say okay. All right. Good. Good. Now you see that. Now we are in. We can select the group. Select a group, and it's going to be a manual group, a manual group, and it's that center node. Now the center node, my plane disappeared on me. I can always get them back. So let me get it back. Uh, Let me see for a second. Okay, there we are. Okay, so I want to select that center node right there. You see this? Right in the middle. That plane helped me to find it. Otherwise, you have to count these and find out where this point. I created a manual group consisting of one node, and that node is right there because this will allow me to put a force on this group. I cannot put a force on a node in 3D experience, but I can put it on a group. Okay, so we say okay. So we did create our group. It's actually right here. You can see that. If I ever need it, I go there. So we go and do the rest of the stuff. Namely, remember we were in scenario. Okay. Okay. Good. So we already created a finite element model. That's why this red exclamation mark became a green check mark. Now we're going to go do procedures. The first step is going to be frequency step, and I'm going to exact 10 frequencies. Okay, very good. Now we have to apply the restraints. Here is going to be helpful if I hit these uh, uh, elements. Okay, and also don't forget to hide the sketch. It's already hidden. Good, we already did that. Okay, so under the restraints, these four edges are clamped. So here is the clamp. You can see that clamp, one edge, two edge, edge 3, and edge 4. I mean, in 3D experience, it doesn't put anything exotic for you for clamp. It put these big balls, white balls. Okay, so that's fine. Okay. So as far as extracting frequency is concerned, this is all done. Okay. Now we're going to go and do our second step. So we go to procedure, and we want modal dynamic step. This was, oh sorry, not modal dynamics, was video number 8, and this is harmonic response. So you click on it. Okay, so let's see now. Couple of things. First of all, uh, lower frequency we set 100, higher frequency is 300. So we're going to sweep basically frequencies between that range, increments of 1 hertz. Okay. Now, what am I talking about? When you look at the slide here, see we are looking at the fan speed between 100 hertz and 300 hertz. Okay. All right. That's good. And take all the modes, all the 10 modes that I calculated. You say okay. All right. Good. Now we're going to apply our load. Okay, so apply the load, and I'm going to apply a force here. See that? A force right there? A force. I will have to do something. Okay. So the support is that group that I picked. I can't pick a node here, but I can select a group. Okay, and the value I'm going to put a 1 Newton. Okay, 1 Newton. But there's a factor, scale factor, which remember I said it is, we're going to come back to this. The scale factor is 0.0079. Not only that, I need this curve. Okay, so there's something missing because later on I have to go and select an amplitude and I don't have an amplitude. You cancel this. Okay, so first we're going to go and import our amplitude function. So you go to, once again, you have to go to setup. You go to setup right there, setup. There is a tabular amplitude. You click on it. You can type all those numbers, that entire thing, in the spreadsheet, first column, second column, in this table, and add table if necessary. Or, well, first of all, this is a frequency. We know that. Make sure this is a frequency. Okay. And if you right click, it says, oh, you can go and import an Excel file. So import, I'm going to go to my desktop. I'm going to go to the folder that I keep these things. Right there, frequency modulation. Say okay. There, it automatically fills it in. And if you want, you can even plot it. Right click, plot, and I should be getting that curve that I showed you before. Okay, good. So we say, okay, we created an amplitude that we can use in a minute. All right, so now we're going to go to loads, force. The support is that group. I put this node that I wanted to put a load on it in this group. There's no other way. You cannot select a node by itself. Okay, good. You see that? It was right there. Now, the value is going to be 1. The scale, I'm going to have it 0.0079. And the amplitude is going to be that amplitude that I exported. There. Don't worry about these things. We say okay. All right. I think we have done everything. So save it. All right. Now we're going to go to simulate, but before you actually run it, you want some information, you want some data, you want to get data, or you want to plot the something about that middle node, the vertical displacement. So you click on it, additional input, and you don't want the whole model, you want it by group, and the group is this group number 1. The same place that I apply the load, I'm going to plot the displacement. Okay, now I did it there, but it's not the field, it's a history plot. Whatever you want to plot versus time or versus frequency is called the history plot. And you go to displacement and translation and rotation. If we just want translation, actually this will do it, but I think in the book I said translation and rotation, but translation will be fine. Okay, and we say okay, we took care of it. All right, and now we're going to go and run. First of all, do all these pre-run checks. So first one is model and scenario check. This was good. Next one, simulation check. We say okay. Don't worry about that warning message that you got there. This is not even running yet. Okay. But if I want to show you something down here, I will not be able to expand this thing because it's doing something here. But I want to show you there are 2 steps here. Step 1 and step 2. Okay, I'm sorry. Step 1 frequency and step 1. Let me close this thing. See that we have a frequency step 1 and harmonic step 1. Okay, just want to point out there are 2 steps here. You can get it there. And now finally simulate. Now it's going to run. There was a warning message there, but warnings don't bother me unless things break down. It's a bad habit, but we got used to it. Okay. Don't worry about this message down there. See, it says output request in the following step will override request from previous step, which is fine. All right, it did run. There was a warning there, same warning that we saw before. We didn't pay attention to it, no errors. Okay, so what's going to happen now? Give it time. Good. So close that. Okay, let me close this. Nothing exciting here, but this is the undeformed model. So let's go ahead and let's go to the harmonic frequency step. It calculated 10 frequencies for me. The smallest frequency is 179 hertz, and you can look at the deformed shape or displacement. It looks like that. Now, if you want to see the mesh here also, so what we can do is we go to uh, on the under contour plots right there, contour plots, and the last one, and say show me the mesh too. Okay, there we are. Now, these are the other modes. Okay, so this is the frequency step. Now we want to plot the vertical displacement, the amplitude of the vertical displacement of that middle node, okay, as a function of frequency. So here's what we have to do. I don't need this. So you go to XY plot from history, okay, and I'm going to go move this thing down, and I'm going to select the translation. Oops, not rotation, translation, and the magnitude of it. Okay, magnitude means the amplitude of it. And what do I want here? Yep, and then say apply. There we are. Nothing exciting except that what it shows you is at around 180 hertz, 79 hertz, it goes to infinity. We know that because 179 was actually natural frequency. So the amplitude, there's resonance here, and the amplitude becomes infinite. A couple of things. This is not very helpful as it is now unless you change the scale here. Why don't I go and change the range of the frequency from 100 to 300, change it to 100 to 150. So let me close that. So let's go back to frequency harmonic response step and change the range from 100 to 150 so that I stay away from that resonant frequency, 150. If you want 170, how about that? 170. Okay. You say okay. Obviously, you have to run this thing again. Okay. Let's give it time. I didn't check anything because I knew that there was going to be one warning message and no error messages, so I just ran it without doing the preliminary checks. Okay, it's done. Almost. Okay, so let me close that. I don't need this because this is not going to change. These are the same numbers. If you go down here under results, plots, right there, this is the one that I plotted before, and it's deactivated now. If I say right-click activate, it will create a new plot for this new condition. And there it is. Just notice that before at 179 this was shooting to infinity, so I could not even look at these numbers easily. So there we are. Obviously at 179 goes to infinity and then it drops down again. Now there is no damping in this problem. Okay, so let's go ahead and add some damping. So you go to scenario, and under procedures, there's a damping here, damping, and I'm going to do fractional damping. So at the frequency, let's take that first frequency, 179. I think in the book I also do all four are full first four frequencies. I give them 5% damping, but here I will do it differently. I will do 5% just on the first mode. Okay, so okay, in the book I also have these other frequencies that are read from that table. I put 5% on them, but here I just do the first mode. Okay, all right, run it. Oh, I forgot to change the the range. I wanted to change the range back to 100 to 300. So let's not run it. Let's go and fix that too. Where is that? Harmonic response. Change from 100 to 300. Remember we were shooting to infinity before? Okay, so now run it. Without any damping at every frequency, natural frequency that curve shoots to infinity. But here we apply damping, so although there will be peak there, it will not go to infinity and it will be finite height. Stuff that you do in a vibrations course. Okay, I don't need this. Close and right click, activate. There we are. Okay. In the book, I gave 5% damping on the first four modes, and obviously that's going to even bring this thing further down. But here, even if you assume that the first mode is damped, then this doesn't go to infinity. Okay, guys, good luck.